Okay, great. In the interest of time, I'll just get started. We don't need the prints. You can get them taken aside. So yes, today I am going to be talking about enabling multi-material 3D printing, bridging design, and fabrication. So like we mentioned, this will serve as my area exam. If you're not familiar with the format, this is going to be kind of a deep dive into the related works that go into my field, what I'm working on, kind of a summary of where I am in my research. So to get started, I'd like to just kind of highlight the sort of amazing advancements we've seen in multi-material 3D printing capability and how they motivate everything we're about to talk about. So we are able to create these really amazing objects, things like really intricate 3D printing or pre-surgical planning models with these beautiful gradients, these multi-material color gradients, as well as functional parts. So things like robots with directly printed in hydraulics. And this has really been made possible by the advancement of 3D printing and things like inkjet printing. So down here you see a 7-channel inkjet printer. This also carries over to different types of printing modality, things like fused filament fabrication, all kinds of things have seen these awesome advancements. However, how we actually do design over multi-material objects has really stayed static. If we have something like this toy car, if I have separate bodies in it, I'm just going to kind of drag and drop and assign these individual materials onto it. I don't have the capability to dive deeper and say, what's inside the body of this car? Is there an engine inside there? What about a color gradient? What if I wanted a nice color gradient paint job on my car? Or what about multifunction behavior? How do I actually specify how the rubber on the wheels behaves compared to the solid body of the car? So as an overview of my talk, kind of looking at the goals, the first one will be gain an understanding of the historical and technical limitations of multi-material design. So we'll begin by looking at the origins and computer-aided design, rendering's influence on the field. We'll dive into existing methods of representing multi-material objects. So volumetric design, thank you. And then we're going to look at my contributions to the field and future directions that I'll be looking. So to get started, all of this begins really before computers were in the field. So in this world, we needed, we had mass production, we needed the ability to replicate curvature and parts in mass according to engineers' designs. So we developed, objects like this, complex mechanical linkages that we could move around to create things like splines and different curvature. We eventually extended this. We worked at drafting tables. We were able to sketch not just 2D, but also projections of 3D designs. And then when we eventually moved into the computer-aided world, we began kind of in those same means. So perhaps one of the earliest examples of rendering is the Utah teapot. So Martin Newell at the time had this teapot and also happened to be working in a cutting-edge graphics lab. So he saw this teapot, they took it into the lab, he sketched it up on paper, and they eventually took this into a series of patches that they could render as a wireframe. We fast forward a little bit, the teapot is still used as a benchmark across computer graphics. There's competitions every year for rendering the best Utah teapot. And now we have all these crazy different attributes we might model about the object. So we might describe the teapot's texture, its surface roughness, or how it absorbs or transmits light. But at its core, this has kind of gone in parallel to the world of computer-aided design. We have a single material teapot we design on paper. Maybe we do it on a computer screen now. We take rendering and we produce an image. In parallel to this, we also have the idea of computer-aided design for engineered parts. We take a single solid body, we have our sketch that we've made, we give that instruction to some CNC mills, and we produce a part. But what's similar about these two workflows is that we're only really seeing the surface of the object, right? Only peering at what the surface of the teapot is. Yes, we might have transparency or other metrics to that, but at the end of the day, we're still just treating it as a boundary surface. Same thing with our produced part. It's this idea of a single material that we're just looking at. And this kind of brings us to this first idea of homogeneous design. So this is very, very popular through most of manufacturing. We have something like a basic screwdriver. We'll break that up into individual parts and individual production steps. So we might produce the cap, the body, and the actual screw shaft itself. These might be made of different materials or different colors. And then we just simply assemble these together at the end. But there's some weaknesses. If we start moving past what rendering provides and start thinking about the mechanical implications of this, let's say we have a simple tensile dog bone like this, and our manager tells us we've got to put a blue material on one side and a red material on the other, and we're going to stretch these things. Naturally, because of the way we're producing these things separately, we're going to introduce this weak joint. Even if we're 3D printing this at the same time, we're going to have to put it with the blue material and then swap to the red material afterwards. It's going to create this weak joint. On the other hand, what we would really rather do is something like this, where we smoothly transition between these two gradients, or through a gradient between these two materials to form this nice, strong boundary between them. So this comes to this idea of heterogeneous and homogeneous design. So the homogeneous is going to be that separate solids. The heterogeneous is going to be intermixing those or interdigitating materials to be able to create these nice smooth gradients that should give us better results for mechanical applications. So it comes to this big question that'll motivate the rest of the talk, and that's how can we use computer-aided design to express objects with material gradients? So I'll first talk about methods for heterogeneous design, and then I'll talk about translating those into actual 3D printed objects. So to start with, we'll kind of think about this in the rendering context, because it's the easiest and it's most often the first one that people tackle when they talk about these design representations. So what I've talked about up until now are boundary surface representations. So this is like a 3D mesh or a CAD model, right? They aim to describe what the object looks like to some viewer. So maybe we're rendering this with raster methods or ray tracing, but rather than looking at the surface, what we're interested in are volumetric representations where we can actually peer through the object. In the case of rendering, that's simulating how light actually transmits through whatever substance this is and reaches our eye. So two of the major ways we can actually render volumetric data, one of which is ray tracing. This will start with some kind of volumetric data we want to render. We'll have our camera or our eye, an image plane that'll act as our screen, and then we cast rays. So we take all the pixels in our image, we throw them at the object and see what it passes through. We might add things like simulated light to see how the scene illuminates, where our shadows are. But what this provides is really good lighting quality at the cost of speed. Since we have to simulate all these different rays, potentially bouncing off of other things, if we want reflections, it's going to be very intensive, and it's really not applicable for real-time scenes. We're just now on the cusp of getting some real-time ray tracing techniques given advances in computer hardware, but still a long ways out. Another option is 3D texture slicing. So the idea of this is to take our volumetric data set, put that in a section of GPU memory, and then cast a single ray through it and generate these planes at regular intervals that are slices, right? And then we render those slices from back to front to composite an image. So instead of casting potentially millions of rays, we're just looking at one that shoots through it and a bunch of planes that result that we can render back to front. This is very fast, very easy to implement on a GPU. There's hardware built right in to do it. But the problem is it's got poor lighting. We don't have the support for lighting and shadows that we do with ray tracing. So it's going to be kind of a trade-off of when we want to use these. I actually implemented both of these in advanced computer graphics. These are a couple of images that show it. So on one side, we've got the ray tracing method. You can see we have pretty well-defined boundaries, pretty good lighting. For the 3D texture slicing, the lighting isn't as good. We kind of get this halo effect around the objects as we peer through them. But it is faster. So, this might be a situation where if I want to rapidly iterate on my design, I use 3D texture slicing to get a quick render, a coarse render. And then if I want to dive in and get a nice final render, I would use ray tracing to get a better idea of what the object might actually look like when I go to 3D print it. Okay, great. So at this point, it brings up this idea of a volumetric design workflow. So I've talked about rendering, and I'm going to work kind of backwards to the workflow because that's where a lot of the motivation comes from. Next, we're going to kind of dive into how we do the actual storing and representing the data structure of that volumetric part that we're trying to render. So the simplest way to represent volumetric data is with a voxel grid. So voxels being volume pixels. We'll have some kind of resolution we pick in this case, and we can form a dense voxel grid. In this case, voxels can really hold any kind of information we're interested in. So maybe it describes the geometry of the object. It could be other things the renderer cares about, like color or opacity. But the thing you might immediately realize is that the memory is not going to scale well here. We basically have an n cubed space complexity that we're trying to deal with to store all of these individual voxels that may or may not contain interesting information for rendering. On the other hand, we have multi-level sparse voxel grids. So these draw inspiration from sparse matrices or octrees, where they aim to capture more and more information where it's interesting. So in regions where we might have empty space, we will use bigger empty voxels. In regions where we have lots of detail or the design or geometry is changing, we're going to use progressively smaller voxels to capture that data. And the result is the memory scales much better. So perhaps the most sort of infamous case of one of these sparse voxel libraries is called VDB. This is a high resolution sparse volumes with dynamic topology. So this was originally developed by Ken Museth when he was working at DreamWorks in 2013. And it was a reaction to what they needed at the time. So they were using these volumetric data sets, these voxels, but they wanted to push the boundary of what they could render. Ray tracing provides a really great way to display these things, but for actually storing the data, they needed something better. And really what they first looked at were these cloud sort of data structures, explosions, or large-scale water simulations. So these are things that have a lot of structure to them. We want to pass light through them to be able to get a realistic rendering of them. And kind of diving a little bit deeper into how OpenVDB works. I'm going to show all of this in 2D, but it extrapolates out to 3D. But in this case, we've got our object here on the left, and we'll have the kind of voxels we create on the right. So we'll start with some kind of generator function. So in this case, it's an implicit function, just the equation of a circle, x squared plus y squared minus r squared. Using this, we can determine if a given point is inside, outside, or on the surface. So if it's positive, it's going to be some distance away, a positive distance from the surface. Inside will be negative, and on will be 0. And then if we come over to the voxel grid, we can see that smaller voxels are going to be used to store the actual boundary of this surface. That's to be able to capture the detail of the actual surface as much as possible. Where regions where we don't have something changing, we're going to have these larger voxels that cover the sparsity better. We're able to pair this with a tree structure. That's where the hierarchical nature comes. So we can walk bigger progressively down to smaller voxels to be able to do this in constant time to access what the value of a given location is when we actually want to do ray tracing and rendering. The key thing to remember here is that these grids can store anything, right? So in a practical rendering application, you might have several grids. You might have a grid for geometry, a grid for your opacity, a grid for density, all kinds of different things. But there's a problem for us, and that's when we start tying this back to 3D printing. We have a really large volume with really small resolution to deal with. So just one of our inkjet 3D printers we have downstairs has almost 400 billion voxels we need to define in it. If we were to use a dense grid, we're talking about 1.5 terabytes worth of space. That's not reasonable for every single print we want to do. If we use something like OpenVDB with an average of 5% occupancy, we're still talking about 75 megabytes. That's a pretty conservative estimate. Another problem we're going to run into is if what we want to capture are objects with a lot of color gradients, they're going to be continuously varying, right? They're changing all over the gradient, and that's going to result in low sparsity. We're not going to be able to capture that gradient very well without blowing up our memory requirements. Okay, so coming back to this workflow, we've got some ideas for how we can store and represent things, but we know that OpenVDB is probably going to be too slow for these really, really large volumes. Another problem is it doesn't provide actual tools for generating those data structures. It's just a pure representation. So if I want to be able to have reusable components for designers to actually express their geometry and material gradients, OpenVDB is not going to provide that directly. We need to think of this as not just a problem to represent and store that volumetric data, but also one that's directly connected to the design aspect. So that's where this project called Voxel Fuse comes in. Brouwer and Ox proposed this across a series of few papers. The idea behind it is to take some voxel geometric generators. So these could be generators we use to create OpenVDB data structures or dense voxel grids. They include things like common shapes, so cubes, spheres, cylinders, and then they introduce a set of operations to be able to combine these into more complicated objects. So Maybe we can rotate, translate, we can combine things through Boolean operations. We can also do multi-material operations here. So we can blend objects with different materials together. And we can create these nice composite objects with it. Like I said, we can do material compositions. So I can take a single object and say, well, I want this to be 70% of one voxel type and 30% of another. We can also do things like create blending across regions. So we can have these different material regions and then create solid and gradient regions in between. But the key limitations we're going to run into are still speed and memory. At best, we can back this with a sparse voxel data structure like OpenVDB. And every time we invoke one of these operations, we're going to have to iterate over that entire space to update our new design. So if I have a design that's using all 400 billion voxels, if I want to blend it, I'm going to have to iterate over 400 billion things and update it. And then the other one is affine invariance. And what I mean when I say affine invariance is the ability to translate, rotate, and scale an object without any kind of information loss. So over here on the right, I'll kind of walk through what that means. On the left side, I'll show a voxel design workflow like voxel fuse. On the right, I'll show an alternative workflow that we'll discuss a little bit later. So if we start with some kind of geometric object, so in this case, it's parallelogram. It's defined by points, lines that connect the points. We'll sample it at the beginning in the voxel design workflow. So we'll create a set of voxels. We're going to rotate that object. And then if we rotate it back to its initial position, we'll end up getting these extra red pixels you see around the side. And this is essentially an aliasing or a tessellation effect by rounding that happens because it is a volumetric and voxel data structure. As opposed to what we're seeing on the right, because we're performing these rotations as implicit geometry, right, onto the points directly before we voxelize, we're able to avoid that affine variance. So the key is to sample the data structure after you've performed all your geometric operations. So the key insight is design before voxelization. So an interesting or a corollary here is that we need a different kind of modeling. And the question is, what if we could model these non-uniform attributes in sort of an implicit way? The affine invariance shows us that that's true for geometry. It also carries over for material composition. So if we think about the original voxel fuse framework, they had these voxel geometric primitives. What we really want to do is kind of cross out the word voxel there and just have these implicit geometry primitives combined with these implicit operations on them, and then to perform the voxelization later. And another thing, thinking back to the original Utah teapot example, is we had these uniform material attributes for the Utah teapot. We were able to describe all of its texture, its roughness, absorption. But what if we could also describe things in an implicit way like that? What if I could describe how the texture changes over space or how the absorption changes over space? To do that, I'll introduce this idea of functional representation. This was originally proposed by Alexander Pascoe in 1995. And at the time, he recognized that most geometry was being represented by boundary surfaces. So these aim to explicitly define every facet of the geometry. So for this sphere, we will define every quad in a file, and then we will say how those quads connect to describe our object. On the other hand, Pascoe took a more mathematical approach to it. So he looked at objects that were defined implicitly. So in the case of this, we have a sphere. We know in mathematics, we can come up with a function to describe that sphere. So in this case, x squared plus y squared plus z squared, the square root of that minus r, forms the sign distance to that. So given some xyz location, it will tell you where it is. And that's what forms the basis of this functional representation. The important thing to realize here is that FREPs are very, very memory efficient. Because we're not aiming to store every facet of our geometry, we instead capture it in these really compact expressions. All we need to store is a simple function. Pascoe extended this idea in 2001 with what he called constructive hypervolume modeling. So this is another interesting insight where looking at an object, we can define a couple of things about it. We can actually decompose that object into a couple of different categories. So on one hand, we might have geometry, so describing where the actual matter is in the object. And then on the other hand, we have some kind of attributes. In the case of this object, we have a color gradient that goes from our yellow to our blue. The important thing Pascoe proposed was using functional representations for both of these definitions. And overall, he called this idea attribute modeling. So what exactly can these attributes be? Well, I've already defined the geometry, but we can also have any kind of other attribute on top of that. Some things that he proposed were color, opacity, density. Some other things could include temperature, elasticity, multi-material composition. And we can categorize these things into different descriptions. So visual properties might be more relevant to a renderer. Physical properties might be more relevant to our 3D printer when we're actually constructing things. The important thing to remember is that all of these can just be any kind of function we want to do to perform a spatial grade. So if we can come up with an XYZ coordinate, we want to be able to describe what is happening at that location for these different given functions. But producing a function for an entire complicated engineering design is going to be hard. So if we want to have a part with a bunch of different graded regions, perhaps we have a robot or something like that, we are going to need a more nuanced way of actually coming up with these designs and these functions to be able to do that. And the way that Pasco did was to kind of pull back on another piece of early computer geometry, and that's constructive solid geometry. So this was originally proposed in 1975. The idea is to take a pretty complicated geometric object, break it down into a binary tree-like structure until we have these composite or these component leaf nodes that describe some kind of basic geometry. So a cuboid, a sphere, a cylinder. Then we can translate, rotate, union, difference, intersect, whatever we need to build our composite object. In attribute modeling, we use that same exact approach. We take our tree, but we actually also, instead of just modeling the geometry, also model the attributes alongside that. So that provides us with a systematic way of performing attributes on different parts and then combining those attributes together to build these objects. Now, this is a pretty old paper, so we have kind of a lower quality resolution or rendering here, but the idea holds. It's this idea of performing this 3D texturing of these objects in these tree-like structures. So you might be wondering, how efficient is attribute modeling? Can we scale this to our inkjet 3D printing scale? So if we remember, for attribute modeling, we can query our geometry and our attributes. So every time the renderer needs to sample wants to render, we're going to sample these functions. This means we're going to have to walk the tree. So as long as our tree complexity doesn't get too long, and in the case of most designs, we'll have a handful of different nodes connected. And the important thing here is, though, we don't need to store anything except our tree. We don't need to store voxels, and we don't need to manipulate those voxels directly. All we need to do is just sample the tree whenever we're ready. So the answer really is it's fast, right? So some limitations of Pasco's work, what was presented mostly as a theoretical framework. So he proposed this as a way, kind of in theory, doing modeling like this. He did provide some concrete examples, but they were purely for rendering. This largely predates most of the innovations in 3D printing, so we don't have a good way of applying it directly to 3D printing yet. And then it brings up this other question. It's how can designers actually create these attribute modeling trees? How can we systematically define them in an intuitive way for users? So coming back to our workflow, we now have an efficient way of representing these volumetric designs. We're rendering with ray tracing or texture slicing. We're going to represent these hierarchical trees. And that's what comes to this next idea. How we actually do the design is with what we call compiled hierarchical assembly. This is primarily relative to constructive solid geometry, although it can also be applied to attribute modeling. The idea is this motivation that constructive solid geometry trees can get complex pretty quick. If I keep branching off and having different leaves with different pieces, how do we actually have designers specify that in a compact way? But we can say that a tree defines some set of instructions to build an object to our computer, and we can say that a tree is really compiled, where the design can compile from a tree. And we already know that tree structures are pretty easy to write in code and to create, and that's all of this kind of led to the development of OpenSCAD, which is this tool defining itself as the programmer's solid 3D CAD modeler. So this is an open source piece of software that's been around for a few years now. It's the result of a lot of people working on it. It provides this nice UI where on the left, we're going to write some code, and on the right, we're going to generate 3D models. What's nice about OpenSCAD is it provides this custom scripting language that we can use to programmatically define objects. Now it's based on boundary representations, and it compiles directly into meshes. So it's really targeted at traditional 3D printing, but it's nice because it's highly parametric. We can create whole Turing complete programs with for loops and branching to be able to describe how we want to construct our objects. But the key limitation is this is only going to support homogeneous material design. We're only going to be able to define different materials on a body-by-body basis. We're not going to be able to capture gradient structures or what's actually happening inside one of these bodies. So with that in mind, we now have a design interface. So we want to be able to program our designs. Those programs should generate these tree structures that we're able to render. But at the beginning, I said this was about 3D printing. So how do we tie 3D printing back in? It's really a kind of a parallel track. As the designers need to be able to view their parts as they're designing them on a computer, we're also going to need to have some kind of module that prepares our designs for 3D printing. And that takes me to my contribution. So this is a paper I published at the beginning of the year. It's a culmination of a lot of these different moving pieces into a tool called OpenVCAD. So like I said, OpenVCAD is going to encapsulate all these different ideas. So we're going to pull the compiled idea from OpenSCAD, the attribute modeling from hypervolume modeling. We're going to want to do material gradients, we need rendering and functional representations. But the key innovation we add and encapsulate everything together with are these 3D printer modules. So this is going to provide a way to take all of these different design representations, put them together, and get these onto a 3D printed, onto 3D printers. So OpenVCAD describes itself as a volumetric multi-material design compiler. What that means is where explicit methods or where existing methods are defining things explicitly, so using solid bodies, so different homogeneous designs, or voxels, OpenVCAD is going to do everything implicitly. We're going to have distributions, and we're going to perform operations over those distributions. The OpenVCAD acts like a blueprint for these multi-material designs. In practice, we end up building tree structures that look just like this, where we have constructive solid geometry like operations. In this case, I define a cone as a mathematical function, sphere is a CSG primitive, translate them around, combine them together with a union, but then we apply these special multi-material nodes that OpenVCAD provides. So in this case, this is a functional gradient that we apply to kind of blend these two materials together across this whole object. So the architecture functions like this, where we have our OpenVCAD modeling language, some kind of printer configuration, so resolution, volume, materials. This gets passed to a compiler module that takes that into a fabrication file that we can hand to our 3D printer to construct. So that modeling language takes a lot of inspiration from OpenSCAD while implementing some new functionality on top of that. So kind of working inside out with our code on the left and a preview of the object on the right. We have our geometry nodes, in this case, a cube and a sphere. I can subtract the sphere from the cube's geometry, and then we apply this functional gradient. In this case, we're applying a static gradient, so it's uniform across the whole object of 20% red, 80% blue. But we could step this up a little bit. If we wanted to print something like this dog bone, where we have two different materials, we could use a more complicated expression. So in this case, this is some code that uses a normal distribution for material B and an inverted normal distribution for material A to describe the relative concentrations. The important thing to realize here is that these expressions that go in here don't have to be any given distribution. It can be any function of X, Y, and Z, or even other coordinate spaces to be able to describe how we want our gradient. What we want to capture here, though, is that they should always sum up to 1 because they're representing the volume fractions, the relative concentrations of the material that compose that object. So this brings us to the idea of sampling OpenVCAD's representation. This will be core to getting it to 3D printers. We'll start with our OpenVCAD design script, and this will provide us with two different things we can sample, right? We'll have our geometry, so this is the sign distance to the surface of the object, or we can query the material distribution field. So this is going to be a vector of volume fractions. So anywhere I put my finger in this design, I should be able to answer how much of blue or yellow this is composed of. So if it's in the middle, that's 50-50 versus one side or the other. But how do we actually print these designs? How do we go from design into a compiled form that the printer can understand. To do that, I'll start by kind of briefly explaining the different printing modalities we support right now. So on one hand, we have multi-material extrusion. So these are printers that take hard plastic filament, melt them, and then extrude them out of a nozzle. So one way we can do multi-material printing with that is with multiple different print heads. So this is a printer we have downstairs that can pick up these different heads, print with them, place it back, and pick up a different one. So we can assign a different material to each one of these channels and print them out kind of discretely. A more advanced version is called a mixing hot end or a mixing extruder. The idea here is we have two or more input materials that come in. They come into this heating chamber, they get melted and mixed together to form some kind of composition on the outside of the nozzle. And depending on the ratio or extruding of these two relative input materials, it'll control the actual gradient coming out of the tip. To actually generate the designs for these printers, we end up doing traditional slicing where we take in our object, we slice it into layers. These layers will be composed of these individual lines that trace out the shape of the object. This is G-code. The idea is it's saying, for example, in this command, go to this specific location while extruding and then go to the next one. Broadly speaking, we'll call these all toolpath systems. In contrast, we have material jetting systems. So these are a little bit more akin to your desktop 2D inkjet printer, but work in 3 dimensions. So where your 2D printer might drop ink droplets onto a piece of paper, this is going to drop photopolymers and then cure it with the UV light, stacking them into layers. And this printer takes a different type of input file. In this case, it's a stack of images, or a bitmap stack. And in it, we end up saying that each color of the pixel defines a different material channel. So in this case, we only have 2 different colors, red and blue, and we just interdigitate them to create the gradient in different combinations of that, in this case, purple, in the middle of the object. And broadly speaking, we're going to call these voxel systems because they capture their definition of their print files as volumetric data as voxels. So that brings us to this idea of an OpenVCAD compiler module. This is going to be kind of an abstract idea here, but I'll dive into next how we implement that for the 2 systems. So the compiler module is going to take as input an OpenVCAD design, so a tree structure, that printer configuration I talked about earlier, and then we're going to need a different compiler module for each of these different practices. So we're going to have one for toolpath-based printers and then a separate compiler module for voxels. So the OpenVCAD design can be the same for the different printing modalities. It's up to the compiler to resolve that into the correct format. And then our printer files will match that. So in inkjet, we're going to generate an image stack, and then in fused filament fabrication, so toolpath systems, we're going to generate G-code. So starting with the voxel printing compiler, we've got our OpenVCAD design, and remember these are the sort of questions we can query about our design anywhere in space. If we command an export, the very first question we're going to ask for every single voxel in the space is this voxel inside or on the surface? And we know that the geometry query can answer that question. So if it's a no, we're going to fill that with void space. We don't need to print anything there. If it's yes, we now need to pick a material. So in this case, we're going to use a weighted stochastic process. Essentially, given all of our materials that we can sample from the material distribution, use the volume fractions as stochastic weights for this selection process. So in that example earlier I gave where it was 20% red and 80% blue, anywhere in that design, there's an 80% chance that's going to be a blue voxel versus a red voxel. And then we can stack that up into our PNG files, our image files that we hand to the 3D printer. The toolpath compiler, on the other hand, has to be a little bit more elaborate. Since toolpathing requires toolpath planning, which is part of the slicing process, that is the idea of generating the different structures of the object. So things like infill, skins, speeds, applying all the different settings for those toolpath printers, we're going to need a separate piece of slicing software to do that. We're going to interconnect the 2 softwares together. So the first step will actually be to take our OpenVCAD design and generate a triangulated surface mesh. This is throwing out all of the consideration for the material distribution and just looking at the geometry. This can be taken as input to our slicing software, just like we normally would with any slicing software. That's going to slice it into layers, generate our toolpath instructions. But now we want to apply our process parameter settings. So perhaps our printer is one of those mixing systems, and we need to be able to apply the correct ratio of the two materials to extrude that tool path as. In this case, we'll use the XYZ coordinates of those tool paths, give it to OpenVCAD, sample the material distribution from the design, and that'll give us some kind of settings we can apply back. In this case, we now have tool paths matched with their settings. That gets passed to a G-code writer. So in this case, the G-code writer can look at it and say that this has this specific combination. So add the necessary settings onto the G-code to make sure that the composition is correct. And then from there, we're able to construct objects like this that have the material gradient across them. So in summary, we have these voxel 3D printer. We have this voxel 3D printer compiler module. We have this toolpath one. We also have the rendering one, which we view as pretty important because we got to provide designers a good understanding of what's going to happen when they go to print the object. And to that theme, one of the things that I want to highlight that we've developed for OpenVCAD is this kind of studio program. So this is a graphical user interface where the user can write code on the left and then visualize it on the right with the full functional gradients and multi-material behaviors. So this provides a nice way for designers to rapidly iterate on their designs before they take it into the 3D printers. This is really not something that's been available in the space before, because the common wisdom for designing parts for these systems is to manually write a MATLAB script that might generate my print files. Having a cohesive framework for this has been really great for collaborating with different partners in it. It also provides other support, so we can script it with command line. It also provides library support, and that's how we can integrate it into things like slicing software. Great. So OpenVCAD provides an efficient way to represent and design these multi-material graded objects. But what comes next? What else am I going to work on? So one of the things that we really haven't looked at yet is actual mechanical gradients. So we've talked about looking at these objects with color gradients, but what if I want to design an object with a soft material and a hard material? Our printers are capable of constructing that, but what happens when we do that? Well, if I represent this object as volume fractions, I might have 100% blue or soft on one side and 100% hard, or that kind of white-gray material on the other side. And we might have a nice linear gradient between the two of them. But if I go actually sample the mechanical properties of this design, we might find the stiffness does not correlate to that at all. It's going to have a nonlinear response just by the virtue of how these materials will combine together in the printing process. So if we want to be able to model using mechanical attributes instead of just volume fractions, we're going to have to deal with these nonlinearities. So this brings up this idea of physically aware OpenVCAD compilers. And the idea here is that a designer has to encode all of this information in their head right now with OpenVCAD about how they want the mechanical properties to perform. So in this case, they're supplying in volume fractions. OpenVCAD is converting that to print files that are also defining them with volume fractions. Instead, we want to pull that knowledge out into one of these models that actually do the work for us. So in the future, I want OpenVCAD to be able to take in mechanical properties, perhaps stiffness or shore hardness or different mechanical properties, convert that automatically into the necessary volume fractions we need. But that's going to require us developing these models and doing the mechanical testing necessary to make that happen. But what I want to have is this sort of OpenVCAD compiler module that encapsulates all of that, that captures the model as well as the outputs we need for our respective printers. And then another thing I want to develop is more compilers. So we have these three right now. I want to develop those physical compilers. We're also interested in looking at other printing modalities. So this is directed energy deposition. We've gotten some interest in 3D printing with this. This process is a metal 3D printing technology. So there's now 3D printers that are capable of depositing different ratios of different alloys to create functionally graded alloys. So that's something we're very interested in expanding into. And then another angle is simulation. So totally different compiler module instead of trying to render or 3D print, using OpenVCAD to capture how our materials are distributed in finite element simulations, so we can get an understanding of how our mechanical parts might behave in our designs before we print them. And with that, I will take any questions.
Well, explain the directed energy deposition by an
Yeah. So there's various flavors of DED, is what it's called. The ones that I'm talking about right now have some kind of powder they bring in. They lay that powder down and they'll use some kind of directed energy. So they can be lasers. Usually these things are printed in completely inert environments. So we'll print them in like a vacuum chamber or something like that. They'll fire it and they'll fuse those metal powders together and then stack them up layer by layer. The key innovation now that we have is being able to do not just a single powder, but different powders, kind of like we did with the inkjet printer. Instead of laying down droplets, we lay down different combinations of different metals. So a certain titanium versus a different steel or something like that.
In what kind of energy does it actually take to fuse that?
I don't know off the top of my head the like amount of joules that go into it, but these are extremely high power lasers that do this. Extremely high temperatures. They're melting these materials and fusing them. So I don't remember the wattage of the lasers off the top of my head.
It's hundreds of watts.
Yeah, it's like hundreds.
But with small focal sizes, so the energy flux is reasonably high. They also use small powder sizes, which reduce the energy required.
Yeah.
Don't you also have all sorts of problems that, if you do that kind of energy, doesn't it heat up and the clothing stores and
Yes.
there's all kinds of problems with that, isn't there?
Yes, and one of the interesting things actually relates down to this bottom box is to do DED really well, you want to simulate how you're printing it, where that laser's hitting, to optimize for not moving the laser back to the area that might still be cooling, right? So this is another reason we're interested in applying simulation so deeply into the 3D printing process, is because while we're printing to maintain quality, we need to make sure that we don't have too much heat concentrating in specific parts that might result in cracking or unintentional porosity, especially as we move toward these like multi-material DED parts where we might have materials that behave differently at different temperatures.
So how do you get the powder there, and you shoot the laser, doesn't the powder dropping get in the way of the laser?
So they have different techniques for dropping them down. They generally use these special like recoders that will go down and actually lay down the powders themselves. So usually they lay down a set of powder and then they'll come over top of it and laser, kind of as a 1-2 step. So they'll lay down powder, they'll laser back and forth rather than trying to hit them at the same exact time. I'll pass these around. This one is that example I showed earlier where we have a perfect linear gradient across the two of them, and you can feel it's not very linear mechanical properties. This is one that I've manually normalized. So it feels much more linear because I use my intuition to make a more linear gradient. Yes.
Some of the objects that may not be symmetrical may be hard to functionally specify.
Mm-hmm.
So, for example, for those things, how much do you think these new advances in computer science technology, such as diffusion models, can help enable novice programmers to specify 3D designs? And also, how do you think like some other technological advances like Gaussian splats and NURBS being used to represent the 3D structure?
So there's two, I think, answers in there. The first is when it comes to modern advances with things like diffusion models, I actually think the answer is probably more related into large language models themselves, right? Because we're defining these things as a scripting interface. And we know that large language models are really good at writing code. So one of the directions we've talked about is using kind of advances in AI to be able to generate the scripts that generate these files automatically so that I can give natural language to it and then acts as a kind of interface so I don't have to write all the code myself or the complexities. As for your second question about kind of where the advanced sort of differentiable rendering world exists in there, we're very focused right now on like the mechanical properties. There's a whole other subset of this field that I didn't have time to dive into that is about visual rendering, especially with these inkjet 3D prints like what I'm passing around. There's a lot of interest in 3D printing these things with really, really good color accuracy. They want to 3D print models of people. There's actually an animated movie they made recently that was kind of like a claymation style, but all of the people were 3D printed. With all of that comes this idea that you need to have something that is very, very visually accurate. And that's where they're using differentiable rendering. The idea is they can take a picture of what they want, develop a proper 3D mapping of that, and then use things like NURBS or Gaussian splatting to be able to optimize and do the differentiable rendering itself to make sure that looks exactly like how we want it to. But for our work, we're looking at the mechanical aspects, which I think are in some ways a little bit behind that. I think we might eventually be looking at that, but for right now, we're kind of more in this stage where we develop a model for our material compositions and use that. Yes.
So are you familiar with OpenFab?
Yes.
Okay, so what would you say would be the key difference between the VCAD?
Yeah, so OpenFab uses these like phablets to describe things. That's the term they use. But the problem with their like kind of phablet-driven architecture is that they have issues with conflict resolution, right? So using a more traditional compiled workflow like this, if we have two materials that might come together in OpenVCAD, it's very easy to say, blend across them. In OpenFab, if I take those two materials and put them next to each other, I can deal with material conflicts, right? OpenFab might not know how to resolve that, especially if I start overlapping those two different material regions. I've got to go in and manually specify, like, this is how I want to resolve that conflict. So in the design process, it's a lot more manual and tedious because of the conflict resolution. In a compiled architecture like this, it's sort of implicit in how you define the object, how like there's a well-defined set of rules for how you handle those conflicting scenarios.
So I'll ask a kind of question. I didn't understand your explanation. What is a fab?
So OpenFab uses, they model with these like phablet ideas, and the kind of, it's a fancy term they use. The core idea behind that branch of volumetric modeling is to use functional gradients and things like that, but they describe it in a much more interactive way. So instead of writing code, they proposed more of an interactive sort of interface way of defining these objects. The phablets they're not exactly voxels, but they're akin to like a volumetric unit that go into them that actually describe the different parts of the object. The problem with resolving them is that if I have two that come into the same area, I basically got to pick one to say, like, this is what I want to use in this specific area.
So do you specify stuff on a voxel by voxel basis, and then you have to interpolate between voxels, or is it a solid object that you need to interpolate, or how do the results?
It's more like modeling with the separate solid objects, and you assign gradients to those different objects. But the issue is when you perform a union, right? When you take those objects on top of each other, what happens in the intersecting region is where things get messy in OpenFab. Yes.
One of the arguments for gradient-based printing is that it's less fragile than the sticking of two items. But then when you're printing it, actually, it's layer-based. So aren't many layers worse than one layer?
So one of the key things to remember in 3D printing is we have like a printing direction. So we're building layers like this across the z-axis. And yes, when you if you print that dog bone, you're always going to want to print it laying flat with the layers because between the layer bonding is a weak joint, right? So like if I take like this object, right, and I pull on it like this, it's going to break a lot faster than if I pull on it sideways because we're going with or against the layers. So when we talk about these material gradients, we mostly talk about them kind of graded in the X and Y axis, kind of because it's the easier toy example to talk about. But as we get into like interlayer bonding, that's kind of a separate branch of research that like people look at is like, how can we improve interlayer bonding? But if we know that we're printing with materials that are two very, very different temperatures. So for example, an ABS is going to print really hot. That's a high temperature material versus a PLA, which is a lower temperature material. If I want to create a gradient across it, let's pretend this white is the hot material and the blue is the cold material. Having a slower transition layer to layer with those temperatures is going to result in better layer bonding than if I try to deposit a hot layer on top of a cold layer. It's about the gradual changes, right?
Can you say more about the physical compilers?
Yeah. So one of the big motivations for this, I have a bonus slide prepared for this. You've unlocked the secret level. This is a paper that was done by somebody else in our lab recently that looked at this in the context of our inkjet 3D printer. So what they did is they took soft material, so kind of like the soft material in the lattice I just showed, a rigid material like that, but also printing with a liquid in there. So these three different phases of material, and then did an inverse design challenge with it, right? So they wanted to be able to say, given specific mechanical properties, in this, in this case, elastic modulus, elongation to failure, toughness as mechanical properties, how can we specify those and then determine the necessary volume fractions to do it? Right, so this is the first direction that I will be looking at when it comes to these physical compilers. We'll be taking kind of the set of equations we derived from this work and then implementing that into a compiler itself. Now, there's some complexities to this. Most notably is the concept of, well, this all works for an inkjet system, right? But I said that an open VCAD design should be able to be compiled across different systems. Right? We might not be able to achieve these different mechanical properties on a mixing FDM printer, right? It might only provide us the ability to grade toughness. So one of the things I'm interested in is coming up with an architecture that aims to describe what a 3D printer is and how it can achieve these different mechanical properties, and have the compiler tell you that if I give it a mechanical design that grades across all three of these different mechanical properties, can it actually achieve that, or is that not something I can do?
Trying to formulate my questions.
Maybe we could ask.
So if I understand it correctly, what everything basically boils down to is that every point in space, all of these other models, they just have to translate that to so much of this material and so much of that material, right? And it shouldn't be restricted to just two, right? It could have multiple.
Right. In the case of this printer that prints the inkjet, or this inkjet printer, it can support 7 materials printing out of it, including some that are soft, hard, and in this case, liquid. This is probably the craziest set of material combinations available on the printer right now. That's why we use it for this mechanical process. Yeah, it's a combination of other methods are more limited because of that. And the design representation has just not been scaled to the levels necessary for this kind of 3D printing.
But in terms of what you need to finally tell the printer is it's just what fraction of each kind of material, right?
It's actually what material to put down at that location. So let me go back and show you a picture. Right. In this one, if we zoom in, this is literally a layer that'll get put on that inkjet printer. We can describe the relative concentrations in these squares, right? And we might say that this is, 80% blue, 20% red, 50-50, and vice versa. So in the case of these inkjet printers, we're actually interdigitating these droplets and relying on the fact that they're very, very small, that when we kind of zoom back, we get the desired color gradient or the desired mechanical properties.
So, okay, so given that, I think when you were talking about the open VCAD setup, you had as part of the compilation, basically randomness as part of the distribution there. So this is when you were saying like 80% blue.
Yeah.
So given that, if I feed your system the same essentially specs twice, I should get 2 different things that have the same distribution, but may give me different mechanical or.
Yeah, so one of the things you can do in Open VCAD is control the seed on the random number generator, and that's just for replicating things in the most scientific way possible. In the grand scheme of things, we haven't delved in the answer to that question, like how much would it actually vary? Given that even this zoom in is like an understatement of how small the voxels are, I think there's probably actually relatively little variance in how much the randomness actually affects it, because the voxels are so small. Each individual voxel is contributing so little individually to the mechanical performance. It is when we zoom all the way up, but you can't see it to prevent that from happening.
Yeah, because I guess thinking about that other slide you were just on, the secret, So thinking about that one, it seems like a lot of basically the liquids, right? Because they're acting as a bulk material in that, I don't know how the liquids are formulated, but their properties are consistent and you're basically filling space. So it seems like most of the, the variation in gradient there is coming from the fact that you have a liquid like different viscosity and.
Yeah, so the liquid, Interestingly, the liquid that gets used in there is actually the cleaning fluid in the printer. And there's a whole other subset of research that kind of predates it. Rob did a lot of this research initially on the liquid printing itself, in sets of rules that you have to apply for that. So for example, for this liquid printing, if I wanted to just print a simple sphere of it, right, and incorporate, 5% liquid, there's already design rules we have to follow to make sure that's even printable. So for example, we don't want any liquid on the surface of the object because it's just going to leak out. We have to retune it, right? So there's some rules that come to like how much liquid we can place where. And if we start getting too much liquid in there, we've got to follow those rules to make sure, which is another branch of like future work we're interested in looking at, is like how can we inform geometric rules for certain things like that.
Yeah, I think my brain is going towards like, the liquid to me seems easier to think about because it's gonna flow into the whole object or its cavities, but when you're spatially varying those two materials, I think in my head, the challenge is, along with that randomization, it's like, it's not clear if you will get the same properties, and the space for those properties is definitely not linear, right?
Yeah.
So I think I'm interested in the physical sort of compilers and simulation, because I think that will be kind of the beefy challenge, right?
Right. I envision some of these physical compilers, like I show them as, just like a model we plug in, but that model could be something as simple as a lookup table for something really simple, but as complex as a full finite element simulation for something a lot more complicated, right? To be able to understand how our part's going to actually behave.
Just one clarification, Mike, just so if you look at the panel B there, it can be a little bit counterintuitive to think about what's happening with the liquid. There's only a small corner of that ternary plot. Those ternary plots, by the way, maybe themselves are a little confusing, but they represent an equal volume mixing ratio between 3 different constituents. So any location in there is a sum of 1 in volumetric occupancy. And so if you're all the way up toward the top, then you have almost entirely liquid in the print. It's only in that regime that your intuition for kind of flowing applies. Everywhere else, the liquid is in a small enough volume fraction that it's mixing together with the other photopolymers that do have photoinitiator and monomer in them. And so everywhere else, the peg that's in there is basically modifying the polymerized structure of the resultant composite and creating an intermediate mixed result. So when these things go down, they're droplets of material. They're only about 75 micron across. That means that they both kinetically and through diffusion mix together relatively rapidly. And so you can, at print time, create on-demand composites rather than things that stay discrete. So for this particular work, which are previous PhDs that we did, we printed every dot that you see in there at least 3 times and did a bunch of mechanical measurements on them to characterize them, and then developed a model which tells you what volume fraction you need to produce a particular mechanical property piece. So Charles's one direction we might go is for Charles to build on that and incorporate the ability to actually deterministically print desired mechanical properties from composites sort of live.
So the output of, I guess, in this paper, would you fabricate to run the test, right? So I see we made like some or something, but
Combination of dog bone and compression test samples, depending on how stiff they were.
and not, well, I guess in those cases for, each one of those dots in C, you would apply the same sort of mixing ratio entirely across the dog bone.
True, but every sample was random. So of the N samples that were repeats, they all had clean patterns.
The rest of us should leave now, right?
Yeah, does anyone else?
You show the rest of your beautiful samples.
Oh, yeah, if you want to look, you can see here, if you want to pass this around, you can take a keychain. The blue ones are flexy and have like a mechanical gradient, and the clear ones just look cool. Some other cool parts in here, if you want to look at, are this airplane wing sort of infill. Looks cool. This is my homage to the Utah teapot. It's got a nice color gradient to it. See what else is in here.
These are,
We have to print every week to keep the printer.
No, those are-
alive.
okay.
Yeah.
Like,
You're like, that's incredible, yeah, that's a, yep. That's the,
While we're here, I was just curious how the materials that you work with are, like, how far are we from making actuators out of those?
say that again,
Like the materials that you're working with, do they conduct electricity? Like, I was wondering how far we are.
So-
from making-
there's a whole other branch, there's a student in my lab who is deep into this question. Yes, you can inkjet print, especially these conductive materials. He is deep into printing circuits and especially flexible circuits with that. The overall goal of the lab are like 3D printed robots, right? Like where everything could be printed and it walks off the printer. Right, so like that's the pie in the sky, like lifetime achievement for Rob here. My part in that is this design representation, right? But there's some very interesting stuff in the like 3D printed electronics space too.
what printer, inkjet printer, so
Stratus J750. This one's kind of fun. I made this in this confab class. This is technically represented via open VCAD. It's a variable density infill. As defined as VCAD. Excuse me. You guys don't have to say.
Seems like they're gonna be something.
Yeah, they can play with the parts. You guys have to leave. Sorry.